Hello, everyone. I think we have a slight camera issue for a moment there, but I should be with you in a second. Welcome to the 30th Surface Ventures keynote webinar. Please do say hello in the chat and tell us where you're joining from. Apologies for the camera issue, but my name is Dr. Sam McManus. I'm the event manager here at Surface Ventures. We are a non-for-profit organization, and our mission is to provide world-class material science education for academia and industry. Today, it's my pleasure to introduce Dr. Daniela Rostohar of Coventry University. Daniela is an assistant professor at Coventry University's Institute for Advanced Manufacturing and Engineering. Daniela formerly worked in several laboratories, specializing on laser process development and machine prototyping. She was in charge of developing the first European laser shock peening system. They used a diode pump of +10 joules for the laser system. I'd like to say thank you to today's partner, Pulsate. We'll have a short presentation from them later in the event. As we go along, please do type your questions into the chat, and it will be marked for the Q&A session at the end. We're planning for going for 60 minutes in total today, and we'll be sharing a link for the attendance certificates later in the event. So without further ado, let's welcome our speaker to the stage. Daniela, please do come online.
Hello, do you see me?
Hello, yes.
Should I share my screen?
Yes, please do.
Okay. No, I don't see how that's possible. I don't see
just the sharing button.
I don't know what I'm sharing. That's the problem.
Okay. Nothing. I don't see anything yet. So I think if you share your just your whole screen, and then
just let's try like this.
Not a problem. Okay. Whilst we're waiting, everyone in the audience, let me just release our preliminary poll question for you all to answer. So we'd just like to ask, what is your current position? We'll have several other poll questions throughout the event and also some handouts as well.
I think now I'm sharing.
Yes, I can see that, Daniela. And yep, we've got the laser pointer. Fantastic.
Thank you very much.
Thank you. I'll leave stage
Sam, for introducing me and giving me opportunity to speak today about laser shock peening. Very nice laser-based technology. And I will be speaking mostly about this technology from point of view, what is important from laser parameters and why we need certain kind of special parameters there. Here is the overview of my talk. I will be starting with the introduction of laser shock peening, and I will be speaking on something what is targeting so-called high energy per pulse and low repetition rate regime. I will be explain influence of different parameters on laser shock peening. Then I will be sharing with you a little bit of experience of developing a first European diode pump high energy nanosecond laser system, which was adapted for laser shock peening, and also speak a little bit about how laser shock peening station was developed, and show you some interesting application. And I would finish with my view on future work. So a little bit of history. Laser shock peening started to be implemented more or less quite in the same time, almost in the America and in Japan, for two completely different applications. In America was implemented by GE in order to solve so-called foreign object damage, while in Toshiba was solving stress corrosion cracking in reactor vessels. After these two companies, very soon after that, was established first metal improvement company, which is now Curtiss-Wright, which is offering mostly laser shock peening as a service. And we have one of their cell inside of Rolls-Royce, for example. And laser shock peening technology, for example, is also an American company which is nowadays offering the machine for laser shock peening. So laser shock peening is surface enhancement treatment, which is allowed you to increase a lifetime of critical components up to 10 times. It's going or imprinting residual stress 10 times deeper than other surface enhancement technology. It's helping you to prevent costly failures, decrease downtime, and enable usage of lighter materials. I'm just listed down a different kind of industrial sector where laser shock peening was tested or it's already implemented. So, as I said, I will go on to speak about laser shock peening in high energy and low repetition rate regime. First, I would like to say that laser shock peening is cold working process, meaning that you are not melting the surface with this process. And this process is plastically deformed material and imprint deep compressive residual stress. When I say deep, we are speaking about more than millimeters. How that's looking like, you have your workpiece, then you put a so-called sacrificial layer. Here is the black tape, usually a vinyl one. This tape has two rows to protect your workpiece for heating and also for being ablate and create the plasma. In this regime, you're using a laser beam, usually infrared in Joule energy regime and nanosecond pulse duration. Once this pulse is ablating this sacrificial layer, the plasma will be formed, and if there is no something what we call confinement media, in this case water, this plasma will be expand, leaving very shallow residual stress in the surface. But if we put water on the top, there will be no space for plasma to expand. Shock wave will be created and propagate inside of the material. So how that's looking in can I start somehow this video? Yeah. I can't start video now for some reason. Okay.
If you turn the laser pointer off for a second.
I'm trying to yeah, okay. So here is the video. As you see, we have the part. Green light is not a laser. It's just light showing you where is that laser pulse it's coming. It's used infrared in this particular case. You have the black tape. There is a water layer. You see the water layer, it's really thick. It's a couple of millimeters. And a laser pulse is coming next to each other, ablating the material. And in moment when plasma is not anymore confined, you see the splashes back. Okay. So what is doing? We have plasma pressure, which is plastically compressed the metal in the normal directions. Metal would like to expand to conserve volume. Then surrounding metal is resist and setting up compressive field. So now, as you see on my video, treating area by moving the laser spot next to each other, you can create residual stress over the treated area. Here I also would like to point that you can use something what we call multiple sequences. Then basically you put a one tape, you treat with overlap or no overlap, then you remove the tape, you put a new tape, and then next pattern it's shifted a little bit. On that way you're controlling how the treatment is uniform around the area, and you also reduce the roughness of treated surface. So I'm first going to point to all of you one of the article which was published already in 1995. And in this article, you can see that for pressure of gigapascal, you need laser power density in the region of gigawatt per square centimeters. Here, first, I want to show you something down on this graph. You see, if we don't have confinement media, as I said, we can put some pressure inside of material. But with confinement media, we're increasing pressure up to 5 times. And in addition, we're increasing the duration of the pressure wave. Why it's important, the duration of this pressure wave? This is setting the time, how long this change will be traveling inside of material, or to be more specific, how deep you will imprint your change. So can we do laser shock peening without confinement? I know there is a recent publication about that. Yes, as I said, we can put residual stress on the surface, quite high level, but will be very shallow. Laser shock peening is a method which is mostly trying to find application where shot peening is not applied. And one of the main benefits of laser peening is capability to go very deep in the material. So the answer here, yes, you can do, but using such a very expensive, high energy laser is, from my point of view, a little bit of waste. Another important parameter, if we look now and say that pressure is depending on power density, everybody would say, okay, let's increase power density to infinity and I get as whatever I want for maximum pressure inside of the material. But unfortunately, that's not true. And it's not possible, as you can see from the graph on the left side. Around 8 to 10 gigawatt per square centimeter, we are getting some effect which is stopping us in increasing maximum pressure in the material. And at the same time, pressure duration inside the material start decaying. And the reason for that is calling water breakdown effect. How to explain that the best? Water in this particular case is confining media, meaning it has to stay transparent and should not interact with your laser. In the regime when we are coming to water breakdown, meaning that your laser start creating the plasma in the water, this plasma will be reflecting the beam in some cases or absorbing initial energy. Another things which I would like to show you is some temporal energy distribution trick. If you look on this graph, now these squares which are black and white, the black one are showing that we are having this water breakdown, and this is corresponding to so-called Gaussian temporal energy distribution. So the GE put some invent, and it's already patented, when they were able to cut this initial part of the beam on the way that they postponed this water breakdown. And as you can see from this graph, in that way you can increase the peak pressure which you are giving to material. Then if you're looking at just laser fluence or you will see that that's depending from energy per pulse, pulse duration, and spot size. And if we say that we are keeping the same value, but we are changing the just spot size, you can see that we are increasing already 2 times depth of residual stress if we're going from 1 to 3 millimeters. But in the same times, you see you need to increase energy per pulse from 1.8 to 16 joules. not only that you are imprinting your residual stress deeper in the material, larger spot size is also increase the speed of the process. Another, which I mentioned, is pulse duration. And we already saw in previous slides that longer laser pulses, meaning longer pressure waves, which are traveling deeper in the material. And you can see from this graph that this is obviously the case. So here I just want to show you or share with you how the cell and looking for Curtiss-Wright, because we took inspiration from them. Because they are offering this service on industrial level and doing really professionally and nicely. So their laser system, it's having a pulse energy between 25 and 30. They have, I think, even laser up to 50 joules. Pulse duration, they can vary between 18 and 50 nanosecond, and they have this slicing technology to basically temporal beam shaping. They're using repetition rate between 1 and 5 hertz because their laser is so-called lamp pump system. And being very advanced in laser technology, they know that those lasers can be sometimes unstable. This is why you see in the picture left down screens when they are showing the monitoring of every laser pulse, both after the laser and also on the material. And upside, you see probably one of their quite complex station when they have a part mounted on one robot. Water delivery is on the another one. You don't see it. It's on the back side. And a black box, which we see close to us, is a scanner, which is responsible for beam distribution. So if, for example, that question I think was even more complex when we were starting approaching laser shock peening. Can we really buy or find a laser for laser shock peening on the market? So I was putting here beside the Northern Grumman laser, which is American ones, lasers which are produced in Europe. And on the bottom you have two industrial scientific lasers. And first, what you can see from this list is that there is most of this laser have enough energy per pulse, but the pulse duration is very short. And if you remember, and you will see also from some application, which I will show, that the pulse duration is very important and define how deep you will imprint residual stress. Another what you can see like problem with most of this laser, they don't have neither temporal and very often neither temporal or spatial shaping. And from industrial point of view, maybe another important point is that most of these lasers are very expensive. I will show here the BVOY laser. This is the laser that I was involved in developing and adjusting for laser shock peening application. I will not go in detail about this laser. Here I'm just showing these pictures to show how complex, how big this laser is. And for laser shock peening application, we were using only after first amplification. We are not using 100 joules because there is a missing isolator, which stopping reflection of the laser reflection of the light coming back to the laser and destroying the laser. For this laser, we designed something what is called front end, because we know that we would like to have top head beam and with a square shape. And also we wanted to have temporal rising time. That means to minimize the time which laser needs to reach maximum energy. Also, we wanted to have 80% of duration of the pulse in the maximum pulse energy. And for that application was created such kind of and designed as front end. As you can see, it's involving the 4 institutions. And similar to the laser, I will not go to the detail about that, but if somebody is interested, I can provide more information. This is the laser cell we had, and a laser beam. It's coming, maybe I can now use the pen again. Laser beam, it's coming through this tube because the laser is below the cell. And then this is, if you look on that drawing, laser beam is after this mirror, most of the beam going through the system for controlling the spot size. Next to the laser, which is not possible to see on this drawing, we had the attenuator, and this additional small part of the beam was used similar like Curtiss-Wright is using to monitoring the laser pulse, both near and far field. Laser beam, it's then distributed over the sample, which is mounted on the robotic arm. And here is also a water delivery system. You will see more about this system on some videos, which I'm planning to do, to show you. And here are two different devices which we use for measuring of residual stress. For developing on laser shock peening, maybe we were missing something like measurement of fatigue lifetime. So if somebody is implementing laser shock peening, I would advise to have these capabilities as well. So let's show now some of the application. This is tooling industry. And here what I would like to mention, it's very important that you understand the problem which you are treating. In this particular case, there are two problems. One is related to cracking, such as fatigue of thermal cracking, and another one is related to wear. So thermal cracking, we were able to solve with laser shock peening, but wear problem, which is usually solved by increasing the hardness, we were only slightly influencing, because laser shock peening, it's not a method which is increasing the hardness. So the problem in this particular tool was solved by first doing laser shock peening and then putting the very hard coatings. Now I have to switch again laser pointer in order to show you the video how this part was treated. We are treating only this red part which was shown on the image on the right corner. The green light, it's not a laser, it's just a diode light showing where the treatment is done. As you can see, we are using 10 Hz laser, but speed of the process here is mostly defined by speed of moving the parts. So I think maybe to increase the productivity would be better to use very similar kind of arrangement what Curtiss-Wright is using. Okay, and results, you see a tool before treatment was able to work for something like 5,000 strokes, and there was loss of the material of 0.73 millimeters. While after laser shock peening, we were able to increase number of strokes for more than 2.5 times, I would say, and we reduced slightly material loss. Another tool is coming from Skoda, and there, as you see, there is crack propagation in heavy loaded areas, and those areas are marked with a red on the drawings. So in both of this application, I think that what was very nice is that we, since the tools were already in operation, we really know where are the problems and what kind of problems are there. Now I will be running this video. It will be a little bit noisy because I want you to experience how the laser shock peening will sound. So you see the plasma going out and clicking. It's showing that this is really mechanical process. After the tooling, one of the sector which we were looking is additive manufacturing, and all of us are aware how much this technology is very interesting to industry. But at the same time, there are several problems like voids, pores, tensile residual stress, surface roughness. So we were investigating if we can, for example, eliminate tensile residual stress. Can we increase part performance by mitigation near surface porosities and allowed those parts to be used in more sensitive applications? We were also trying to improve the roughness, reduce the manufacturing time by using the thicker layer in the printing, and also if we can increase the cost by or minimize the influence of the powder quality. So here I'm showing the data on LSP on additive manufactured stainless steel. And from the graph, you see that we were able to imprint residual stress quite deep, over 1 millimeter. And in fact, it's this, if you look at the grain size, you see that we significantly change grain size, make them much smaller. And after that, we did a fatigue measurement. AB is built. This is originally parts, while the another two correspond to laser shock peened samples. And the difference is that in one case we used vinyl tape, another one aluminum. But in all cases, you can see that we were able to increase fatigue lifetime or time when we start detecting the cracks. After that, we start working also on titanium alloys in cooperation with Memphis University. And what you can see here, they were printing parts like that using the two different methods, where the one of them corresponding to more optimized and another one to less optimized process. The green is obviously representing the less optimize the parts, and we pin those kind of samples, and then we perform fatigue lifetime. And you can see that for all of these samples, we were able, depending on the load, prolong the lifetime. And for example, for certain one, we were able to prolong lifetime up to 100%. So even for less optimized process, that was possible to improve the performance. As I said, we was also working on possibility to minimize the time of the printing. So we increased the layer of the printing. So all of these ones are without laser shock peening, while this one with full sign are pinned. And obviously the best performance we had for most optimized EOS process on which we add laser shock peening. But you can see that, for example, for this 60 microns printed, if we do laser shock peening, we were able to get very similar results like for other MEM or EOS optimized processes. So in the conclusion, I would like to say that you need to think about what are the optimum parameters of your laser you should use. I would say in this regime, it's good to have 10 plus Joule, because that's allowed you to play with the spot size and also allowed you to do a faster process. Pass duration is very important because, as you see, defining how deep you can go in the material. Repetition rate, we were using 10 hertz, and as you see, that was not one of the limiting factor in the speed of the processing. Then I think what is really important is this temporal and spatial shaping, and I wrote here like rising time shorter than 1 nanosecond, and the falling time less than 2 nanosecond. You need to have minimal fluctuation of the energy in the maximum. You should have no pulse-to-pulse energy fluctuation if it's possible. And the top head square beam give you a lot of opportunity to better define your sequences. But still, as you see, even with the less optimal laser parameters, if you do proper this temporal spatial shaping, you still can find application where you can benefit of using laser shock peening. If we are speaking about further development, I see them mostly in the photonics, because we are, as I show, we are missing still suitable laser on the market. And another things which we are also missing is fiber beam delivery, which can be of use for treating maybe in servicing, and maybe also parts which is difficult to approach. And we are also missing solid confinement media because there are still a lot of applications which are not allowed to use water. I want also to show you some little bit of work on the small size laser. We were trying to see if we, based on the knowledge which we learned from developing the big laser, if we can build a small one, which is portable and being able to work. And this first prototype had around 2 Joule and 10 nanosecond. And the repetition rate was 10 to 20 hertz, and it's a diode pump system. And what you can see, for example, that from stainless steel, we were able, even with such very tiny and cheap laser, to get significant residual stress on the surface and go relatively deep in the material, both for steel and aluminium. Maybe it's interesting why we try this shape of the beam. We were testing if this will give us better treatment of some special 3D geometries. And now this laser will be upgraded to go up to 5 joules, having the longer pulses. Also here is liquid nitrogen cooling will be changed to water cooling. And maybe what is most important is this laser has a very small size. And in the end, as we discussed before this presentation, I would like to say special thank you to the people who are really helping team in Prague to very fast adopt and develop this method. And this is different pioneers and people who develop this method. And I advise all of you to either approach them, either look for their papers, because they're explaining and can guide you through this method. With that, I would like to thank you, and this is end of my presentation.
Thank you very much, Danielle. It was a fascinating talk. We got plenty of questions myself, but before we move on to the Q&A section, we'd like to welcome Dr. Pratik Sukut to the stage, who will be delivering a short presentation on pulsate.
Thanks, Sam.
There are your slides right there.
Okay, so yeah, thanks for that. Hello, everybody. I'm Pratik Shukla. I'm really presenting this on behalf of Pulsate, and my organization is the MTC. This project is really to encourage and support laser-based additive and advanced manufacturing within the European network. So the MTC, where I work, is very active on this project. So just for those who are not aware of the MTC, it's a research technology organization based within the UK, on the edge of Coventry, and it was opened in 2011, and it's really there to bridge the gap between academia and industry. So it supports systems and solutions in manufacturing, and also provides training and skills development. So as a for those who are not aware, there's some on the call who do know me. For those who are not, my background's in laser materials processing, and central to that is surface engineering, and more central to that is laser shock peening. So yeah, it was a nice, interesting talk from Daniela, and I'm always interested in that topic. I am also an editor in chief of a journal called the International Journal of Peening Science and Technology, and a founder of a company called Bright Beams Laser Technology that's commercializing portable laser shock peening systems. So going back to Pulsate, it's a multi-organization uh, consulting project led by Amons in Spain. They're a laser center, and the other partners include Sintef in Norway, CEA in France, Fraunhofer in Germany, Center for Physical Sciences and Technology in Lithuania, the MTC, which is where I am based in the UK, Funding Box, Epic, and ClearGo. They're responsible for managing the funding and the dissemination. So all of these partners got together several years ago to apply for the Horizon European Horizon 2020 program, which is where the core of the funding is coming from to support this this project. So Pulsate is there to foster pan-European collaboration, empowering SMEs to grow their capabilities in laser-based additive, advanced and additive manufacturing. So it includes providing technical advice, guidance, funding support, as well as route to market for new technologies to cut the to simplify it really. So the markets covered by Pulsate, they're not limited to this, but they're focused on aerospace, which is where, for example, laser shock peening challenges are addressed. Medical devices is another market, industrial machinery, automotive, customized electronics, textiles, and clothing. So the idea is to encourage and apply laser-based advanced additive manufacturing in these markets to address burning issues and challenges, and help technology development from these sectors. So the final product of Pulsate will be to create a digital platform called the Pulsate Digital Agora. So stakeholders, industrial partners, technology providers would contribute to this to build this platform, and eventually functionalities such as collaborative partnership, matchmaking could be offered to people associated with the Pulsate program. Also educational material for laser users, advertisement for laser-based technologies, and any funding opportunities that may arise as well. So who can join? Well, if you're a service provider, equipment provider, an educational institute, a stakeholder interested in laser-based technology can join and contribute to this domain. There's various grades of membership available as well, so it goes all the way to gold membership, and respectively, the benefits obtained for that membership are different to, for example, a free membership, but it's there for people to contribute to. Now, Pulsate in the recent past has been offering funding support for 3 months, for example, 25k in euros, and I think there's been a couple of calls there supporting experimental development, proof of concept studies for technology providers, SMEs coming through with new technologies have been awarded this funding, and there's been some success stories, and we can, I can share a few with you. So, for example, a project called Subar, which scaled up a biomimetic anti-reflective surface textures or structures through laser surface structuring, and they were doing this on glass to improve some of their optical microscopy applications. And in doing so, the impact of the results that they achieved for achieving less than 1% reflectivity in both visible and near infrared spectrum. Another project called WellShape, which were offering a new beam manipulation or beam shaping technology to weld crack sensitive aluminium alloys and hard to weld materials in general, and they were able to achieve this with deeper penetration and making the technology more digitalized and integral with other technologies. So again, something that's in the pipeline, that was funded and progress from very low TRLs to from TRL3 maybe to TRL5, 6. The next project on the list is a project called Loomstate, which adopted laser cutting as a replacement technology to their conventional method, which used mechanical cutting methods for the garment manufacturing sector. And in doing so, using smart nesting techniques, they were able to achieve less material waste, reaching near to zero waste, reduce carbon footprint, reducing non-conformance, and manufacturing in a more more smarter way than what they were doing before. So again, benefiting from this program. So at present, there is an ongoing call which people can apply for. So it's a adopters and end users sort of team up call where people in that from that background can team up and apply for this funding to develop specific technologies within the scope of Pulsate. So if you want to know more, feel free to either get in touch with myself or there's details here which you can refer to for further information. So yeah, thank you for listening, and yeah, it's a pleasure to provide this talk.
All right, thank you very much, Pratik. That's very interesting indeed. The link to the Pulsate website is also in the chat if anyone would like to go and look there.
I think it's I think people could get through it straight from a search engine as well. So yeah.
Yep.
Yeah.
Absolutely. So I think at this point, let's open to any questions for either yourself, Pratik, about Pulsate, and Daniela about more generally about LSP. Although, as from our discussions earlier, you both have a lot of technical knowledge of this area. So, but please, you type any.
I'll let Daniela lead the way.
Okay. So before we get any questions in, I'll just release the link for the attendance certificate there. So as always, with this will only be available during this session. So please do download that or click on the link now if that's of interest. While we're waiting for any questions, I think I'd like to sort of start a little bit of discussion. I think one of the things I was thinking of during the talk when you started talking about them working with titanium alloys, I believe. Daniela, do you need to tune LSP differently for different materials?
Yes, because if you remember in my talk, there was the something which is related to material. The material which are harder, you need more energy per pulse to go deeper inside. So you are tuning the process for each material. And not only each material, you also, for same material, if it's a different application, you will tune the process. This is why I'm always saying, like, you have to start from the application. Either case would be that if you are designing some part and you know that you're expecting some problems like cracks, like corrosion cracking or anything like that, you should thinking how to design your part to allow for laser shock peening and understand what kind of improvement laser shock peening can benefit. Unfortunately, usually people first, like I show in my presentation, people first done kind of design of the parts and then experience problem and then they coming back for solution. That's a possible as well, but sometimes it's complicate and limit capability of laser shock peening.
I see. So with that tuning, I'm just curious what the sort of general process would be. Would it be first setting, say, fairly standard parameters, analyzing how the
We
material,
usually,
sorry.
yeah, for example, the one of the first things is when you're developing the station is to define the ratio between the spot size and water thickness. So there are some optimal parameters which allowed you. So in Prague, we usually work between 2 and 4 millimeters size, 4 by 4. And then you are usually pushing energy per pulse more for material. For example, aluminum, it's very soft material. So you would not go more than 4 Joule, for example. But if we have steel and titanium, we're going to the maximum because it's very hard material and you want to imprint them deeper. You can try to understand laser shock peening. I'm always saying you want to hit with your hammer, and harder the material is, you are taking a bigger hammer, right?
Yes.
It's the same with laser shock peening.
Just to chip in there, if you get a material, you'd have to look at the Poisson's ratio, that the Young's modulus,
Yes.
the yield strength, and work out the HEL, the Hugonot's elastic limit, and then design. And then that tells you what sort of pressure you need because you have to surpass that elastic limit twice, and then you can backtrack by tailoring your laser intensity to
Yeah,
that required pressure.
I think we have this.
Yeah, I think Daniela you showed that in
Yeah,
one of the
I think
graphs.
we can
Yeah.
show this formula back.
Yes, yeah, please.
Yeah.
Sharing that, you can share your screen then. So you would say, yeah, so the pre laser shock peening mechanical analysis is quite key then. So
yeah, that's why it's
Yeah,
very good if you have in the team laser people, material interaction people, and material people, because then you have a team of all three expertise, which are really essential for implementing this technology, I would say. I don't know what Pratek think, but I had a feeling you need to have 3 different level of expertise in your team to be able to do that.
Yeah, and somebody to integrate it as well, to put it together sometimes. So I agree. Yeah, it's a multifaceted technology.
Yeah.
really interesting. Yeah, it seems like it's fundamentally it seems like a relatively simple thing, but as you've been said, well, in terms of what is physically happening, yes, but then of course there's the complexity of running the laser, of understanding the mechanics, integrating all the solutions together. So Seems like it's a
I
bit more
think
difficult than.
you have to understand first what's happening or in creation of the plasma. Then you have to understand how this plasma will be transferred to the shock wave, and then you have to understand what shock wave you're going to do to your material. And then you also have to say, okay, this change will guarantee what I'm looking for. This is what Pratik said. You can go both direction and somehow you find in between. You're going from material side, you go from laser and plasma, and you find some optimal parameters.
So would this technique generally be employed on bulk materials? Has there been any work done on coated materials as well? So say your normal kind of say for the type of research that I've done before, sort of PVD, CVD thin films where we're in the region of tens of microns, would it be?
At least I think this 10 joule or joule level was not useful for that. But we did on the bulk material, for example, combining with hardening.
Yeah.
Because sometimes they do hardening in order to avoid the coatings. Because, for example, chromium 6,
Yes.
now it's forbidden in Europe. So people are more and more doing laser hardening, for example. And then we were applying the laser shock peening on the top to combine these two methods. But maybe this is what I was saying. Maybe there are the application when you want to increase what I would be looking laser shock peening in that particular case, if there is importance that you refine the grain, for example, or if you have some cracks in that coatings, that I would be looking. I don't know what Pratik would look if we thinking about treating the PVD coatings.
It's definitely a bit difficult because the bulk is different to the top surface. So what's suitable for your bulk might not be for your top level.
Even a shock wave like that you can use for delamination and cleaning, because you will create this kind of the wave between two layers, and you can delaminate for example, in one application which we wrote for European funding, we didn't consider using shock waves for cleaning of the coatings, because you are applying the pressure and you just blow, like we discussed for coatings on the optics.
Blast cleaning, laser blast.
They call it laser blasting. In I think military industry in America, it's using for cleaning. Some hard coating to avoid the chemicals.
Yeah, what it sort of came to mind, I think, just related to some of my previous research, was sort of further modification of hard coatings for, say, impact or erosion resistance, where you want something relatively hard as well because of the increase in fracture resistance, but then that increase in compressive stress that you could also achieve by laser shock peening.
But that's probably more application for something similar like Toshiba is doing, because in that case you're going to another regime when you are using millijoule laser with high repetition rate. And I think in that way you probably would be able to control the depth of this pressure waves and don't get them on this interlayer layer between your coatings and bulk material. I would look more in that direction myself than using this high joule level. I think Professor Sano was showing something like they call it tiny, small laser shock peening.
Palm top.
And I think he was mentioning somewhere about treating some coating in nuclear sector.
It's definitely got, well, there's limitations to it as well, because if you've got a hard coating, it's got a amount of grain size. So you could reach a saturation point where you can't get more than what it's already there, because laser peening is not a solution for everything. If you've got a really fine grain size in your coating, then it might be that it's not going to do anything for you.
Yeah, I think some of the
It's hard enough as
yeah,
it
of
is.
course.
That's what I'm saying. You have to think what are the benefits you want. What is your problem? That's usually when we were learning from Professor Manava. He was always saying, first look backwards. What is my problem? And what caused my problem? Is it cracking? Is it corrosion? Is it? And then think very how I'm going to solve this. If it's hardness, something what you have to improve, laser shock peening is probably not the method. But if it's combination of little bit increase the hardness with imprinting residual stress, then yes.
Yeah, there's something I think very important to bear in mind. You said then sort of analyze what sort of properties are required for your application. Yeah, and
Like all other laser-based application, you have to think backwards and have clear idea where and how and why you're applying this methodology.
Yeah.
Because this methodology is not cheap. And as I said, require a lot of expertise which are missing on the market. So you have to be very smart. And also a lot of people in Europe, especially, it's very worried about patents from American side. So this is also by implementing, you should be aware of that and study those kind of patents that you are not crossing someone already know how. You can avoid that by paying interest to owner of the patent, but you should be aware of that this is very highly patented technology and highly protected American military technology as well.
I think 20, that's one of those 20 researchers out there. Take care before beginning.
Yeah, it's okay. They will not stop you to do research, obviously, but you can't buy the laser from America so easily. Let's say like that, with all properties which I mentioned in my talk.
Daniel, I have a few questions, but I'll let everybody else ask if there are questions.
Think we haven't seen no questions in the chat, so I think it's like we've probably answered most people's, I think, burning questions. So it's continued the discussion for a few minutes.
I was gonna. Yeah. So Daniela, what is your view on using alternative confinement? There's a lot of drive. People are trying to get rid of water, or well, there's a group of people who are okay with water. Then there's a group of academics and maybe a couple of industries who do not want it.
The laser shock peening originally started without water, started with glass.
Yeah.
And the glass is working better than water, but it's not flexible.
Yeah. It's not
That's
flexible. It's not
if you are treating
3D.
2D object, which, for example, I didn't put this very nice application of doing laser shock peening between layers of SLM, and they're using the glass, for example, inside the machine.
Yeah.
But I think it's needed for water. It's messy. Even if you can live with that, it's messy because required a lot of technical solution to prevent water splashing back to your optics. And once this, especially in this application, when you have Joule level, once the water splash back, your optics is burned.
So, I agree.
I think it's a good kind of research topic. I know that the guys from PIM were investigating some kind of polymers.
Polymers, yeah. So that's been ongoing for a while. I mean, I've been doing polymer stuff as well on 2D, and it does good. Actually, works well. But you have to. There's a lot of consumables involved because if you're doing 2-3 layers, you got to replace the polymer. So you're wasting a lot of material if you got a lot of stuff to peen.
I was always thinking, and because a friend of mine is working with gelatin, which she used for optical
Yeah.
properties,
Oh, yeah.
and I was for
Yeah.
a very long time was thinking why we don't just like on the cake put the gelatin
Yeah.
because
It works. Yeah.
it's a cheap and you
Yeah.
can even dope with certain kind of like she's making holograms out of gelatin, so she's doping the gelatin to have certain optical properties, and gelatin
Yeah.
she's really buying gelatin which we are using for cakes. So that was one of my idea, like why not gelatin, putting the layer of gelatin and make machine which is printing gelatin, and it's a biodegradable material, there's nothing poison
Mm.
there, and you can
Mm.
easily wash if you need or peel out and so on.
Yeah. It, the yeah, and then there's drive around gas-based confinement. I'm not sure how effective that is, but there's a big push with certain groups, and I'm curious, but it's and it's very dangerous
Yeah,
too, putting that sort of setup together.
yeah, it's also
Uh,
magnetic field confinement and all of that.
yeah.
And water, it's so simple and easy because you can
Exactly.
in Prague we made the circulation system. We didn't waste water. We cleaned it and
So
then
it was
yeah,
filtered. Yeah.
filter.
Yeah. Yeah, this was the other question. So if you've got so usually we use deionized water. Once the water is in contact with the plasma, it ionizes. Um, so you would reuse new deionized water,
We didn't use
properly
deionized water.
if yeah. But yeah. So with city water and deionized water, I don't think there's much difference, but I'm not sure how much there is.
There is a
And
work
usually,
of Daniel Glazer from
yeah, and then
they
yeah,
did the work.
South Africa. Yeah,
South
yeah.
Africa,
Okay.
they show that there
Yeah,
is some tiny difference because
tiny
what is
difference.
happening that with different ions or materials present in the water,
Yeah,
you can
yeah,
create plasma much more easy. But when we were doing this with Vizar, with the help of PIM group, we were trying
yeah.
with both water and we didn't see any difference.
You didn't see much, yeah, because it's easy enough to set up a process with city water coming
Yeah.
in, rather than have a a loop
We
that
used really
could cause.
tap
Yeah,
water. We didn't
yeah, yeah, yeah,
do
yeah,
anything
yeah.
with cleaning all that.
Mm,
Sure.
mm,
Yeah, it's a lot
yeah,
of as Sam said, it's look on the paper very simple, but I would say it's not very easy
Yeah,
method to understand.
no,
sounds like it's
And
yeah,
there are still a lot of technological
yeah,
problems which are requiring to be solved.
lots of
I'm, for example,
yeah,
very excited to see laser shock peening on very tiny devices for biomedical
yeah.
application.
Miniature devices.
mm,
Yeah, yeah,
Biomedical devices like additive printed
yeah,
small tiny ones.
yeah. Thin wall
Yeah,
structures.
yeah.
very
Yeah, yeah. There's
very
a scope
interesting
for
to
that.
see. So I
Um,
think with that we are just past. Oh, we got one question here from Matthew Kermy. So I think we'll I'll read this question out. We'll do that, and then we'll draw the event to a close. So Matthew says, "Good afternoon, Daniela. Thank you for your insight and presentation.
Mhm.
I'm curious whether or not you have any experience with the LSP of materials that have a distributed phase, such as cast irons, ODS alloys, or other metal matrix composites. Would the different
Not really.
phases interact with the LSP wavefront, such as with reflections or interference?"
We didn't done that. I think that there is a cast iron. I think would work quite well. I would say, and I think was used in many
yeah,
application in the past. And
yeah. Cast iron does work quite well.
what
In
is
the
ODS
composite iron,
alloys? Do you know that, Patrick? What is ODS alloys
I didn't see that. No, ODS.
or metal
What's the full
matrix
form of it?
Oh,
compost?
But the
oxide
metallic
dispersion
metallic
strengthened.
element.
Sorry, that's what ODS means. Oxide dispersion strengthened alloys. A metal matrix with small oxide particles dispersed with it
Yeah,
within it. Excuse me.
It's again question why you would like to do laser shock peening. What is the goal of applying laser shock peening there? And if Matthew can describe why he wants to use laser shock peening, then we can think if it's that of usage. Because the using the laser shock peening, I always say don't use it just because you think it's sexy to apply, because it's better if you have real application. But for cast iron, I know it's working very nice.
It works in
It's
cast
worked
iron.
very nice. And I
Yeah,
think
pinning it,
one of the
yeah,
tools that I showed was from cast iron.
yeah.
Perfect.
And
This
actually,
is
you don't even need so much energy. You could do it on around 500, 600 millijoules, and with multiple passes, you can get some decent compressive stress.
If it's fatigue,
Matthew said, is it concerns fatigue resistance improvement on
weld
tempered
bends.
ductile iron? Okay.
I think this is used by the second question from Svetlana. I think it's very nicely used by Curtis Wright. They have very nice pictures showing how the crack is going around the welded parts and increase the fatigue resistance. And for different, this is the real good application. And I think laser shock peening treated all over the welds, it's something what is really, really nice application.
We'll just
I think there's a lot of papers around this
Yes,
topic as
yes.
well. You'll find weldments of LSP of weldments around duplex stainless steel.
that's a yes to Svetlana's question there. Yes, it can. It works very nice for that application.
I have somewhere a picture, and I was thinking to put in my presentation from Curtis Wright papers when they really do laser shock peening on the welds, and then you see how the crack is going around treated area and not entering the LSP treated area. That's one of the very, very nice LSP applications.
Like a great demo. But I think for now, with time, I think we're slightly over time. So thank you very much to the audience for those questions. Thank you very much, Daniela and Pratik, for fantastic presentations.
Thank you.
Lots to think about with this technique. Indeed. Thank you very much to Pulsate for supporting this event. And now from the Surface Ventures side of things, please do visit our website. The replay for this event will be available later for you all to see and comb back through to look at some of those great references that Daniela shared there. Our next keynote will be organized for the 29th of June, so please stay tuned for further announcements. So there's our website, mailing list, and LinkedIn. We have our fortnightly newsletter, Modern Surface. If you sign up to our mailing list, you will receive this. So the next issue will be going out tomorrow for that. And finally, I'd just like to say to those of you in the audience, please do take the time to support this event by advertising these lectures to your contacts. And finally, just say thank you again to Daniela and Pratik.
Thank you.
Thank you very much. Thanks everyone for joining today. Goodbye.
Bye-bye.